In Chapter 9, we will be looking at addition reactions, and if you have encountered ever an apple that contained a worm, it may have come from this moth, which produces a sex pheromone for the alkene that you see there. We're going to be doing a lot of addition reactions in this chapter, and it's kind of broken down by the type of reactions. There's a hydrohalogenation where you add a hydrogen and a halogen across the double bond. We have a double bond and we have hydration, so we're adding water across the double bond. In a hydrogenation, you're adding two hydrogens across the double bond or reducing it. We have a halogenation where we're adding two halogens, a halohydrin where we have a halogen and a hydroxy group, and then a dihydroxylation. Most of these fall into the functional group transformation category, but there is one that falls into the reduction category. This is something that we've already started, but you want to organize your reaction. If you can remember what type of reaction is happening, that will be easier to access that information when you need to do synthesis problems. So we have the 4 different types of reactions. There's functional group transformation, where one functional group is converted to another one. We have the category where it's carbon bond forming. And here we're forming a new bond to carbon. There's oxidation reactions. And oxidation, if you recall, is loss of hydrogen or gain of oxygen. And reduction reactions is the reverse of oxidation. Reduction is gain of hydrogen. So this oxygen gained the hydrogen, as did the carbon down there. Addition reactions can exist in equilibria. If we have a halogen and we do an addition reaction, our carbon skeleton, and we'll end up adding a hydrogen and a halogen across the double bond. And we've seen already that we can do an elimination using a base to get back to the alkene. Addition reactions usually require a low temperature, and eliminations are often higher temperature. So if we're trying to do this addition reaction, we can run this reaction at -30 degrees. Our skeleton stays the same, and we're going to add H on one carbon and Br on the other. So these are the two carbons that were in the double bond. That's where the reaction is happening. So we get 76% yield of that reaction. This is actually a regioselective reaction if you have an asymmetric molecule. So in the 3-hexene here, this was a symmetric molecule, so it didn't matter which carbon the hydrogen and the bromine went on. But here we have a vinylic proton, or this vinylic carbon. So this vinylic position, this is a vinylic position. Vinylic is the carbon that is involved in the double bond. This one here has 1 hydrogen. This has 0 H's. So when we do this reaction, this is the carbon skeleton. The H is going to go on the carbon with an H, and the Br goes to the more substituted carbon. This is the Markovnikov addition. So the H goes to the carbon with more H's. So the Br, or the halogen, goes to the more substituted carbon. And if you were wondering why that happens, we can go through the mechanism in a little bit here. We saw the Markovnikov addition. We can also do the anti-Markovnikov. So if you add HBr in the presence of a peroxide, that will reverse the regiochemistry. When you include the peroxide, the bromine now goes to the less substituted position, and the hydrogen goes to the more substituted position. So this is the anti-Markovnikov product. In this reaction, we first do a proton transfer. The proton goes to the carbon that already has one hydrogen, which is this one right here. So that goes there. The pi electrons are going to go fishing for that hydrogen and grab it. So that leaves this carbon right here short a pair of electrons. So now that has a carbocation. This is a stable carbocation because it is the tertiary position. In the process of the proton transfer, a bromine ion was created. This is our nucleophile, and this is now our electrophile. We can then do a nucleophilic attack at that tertiary center. And we form a bond with bromine. There are two arrows involved here. The proton transfer first from the alkene to the hydrogen. That creates Br-. This is our positive carbocation that is deficient in electrons from the proton transfer, which it now becomes our electrophile, and the nucleophile, which is bromine, can attack there to do the addition. This is the Markovnikov product. If we had the proton transfer and the hydrogen added here, the carbocation that formed would be a secondary, which is less stable. But if we do the proton transfer and the hydrogen goes to the less substituted, then we get a more stable carbocation. There's also X- available in both of those. So to draw the arrow pushing mechanism for this reaction, this is our proton. We first do a proton transfer. The hydrogen will go to the carbon here that has a hydrogen. This has 0 hydrogens. So this puts the carbocation here, plus Cl-. This is our nucleophile, this is our electrophile. These electrons come in here. And that was a nucleophilic attack. When we do this reaction, there is stereochemistry involved. We go from a non-chiral alkene to creating a chiral center. When the carbocation forms, there's two products possible because the nucleophile can attack from the top side, or the nucleophile can attack from the bottom side. So top side attack, bottom side attack. We can have R2-chlorobutane or S2-chlorobutane. Two possible products for that. So give the products of these. The carbon skeleton will stay the same here. H will add to the carbon with more hydrogens, which is this one. And Cl goes to the other. This is a chiral center, so we can draw two products. So this would be the mixture of products. If we add HBr to an alkene that is part of a ring system, the mechanism is the same. The carbon here has 2 hydrogens, this has 0. So this N carbon will get the hydrogen, this will get the halogen. And this is not a chiral center, so we don't have to worry about stereochemistry. Because this reaction goes through a carbocation, a rearrangement is possible. You can have a hydride shift or a methyl shift or an alkyl shift if that makes the carbocation more stable. In the reaction that you see here, there is a proton transfer. The proton goes to the carbon with more hydrogens, this end one. This is a secondary carbocation. And then once the secondary carbocation is formed, the hydrogen that is here can shift over. And our carbocation goes to the tertiary. This was secondary, this is tertiary, which is more stable, and that's why we rearranged. The chlorine is our nucleophile, this is the electrophile. We can do a nucleophilic hug. In these reactions, this is the one that we just did, there can be a rearrangement. To end up with that product. Proton transfer. That's secondary. We'll get a rearrangement to form a tertiary carbocation. So the hydride will shift over. The chlorine acts as a nucleophile, which hugs the electrophile at the tertiary carbocation, and we get the chlorine at the tertiary position. In a hydration reaction, we're adding water across the double bond. In the same pattern, where the hydrogen goes to the least substituted with more hydrogens on this carbon, and the OH part of it goes to the other side. A hydration reaction usually occurs under acidic conditions, which is why we see H3O+, or you can have water plus H2SO4. The product is the same. When you do a hydration, more substituted alkenes will react more quickly than less substituted. Hydrating ethene is low. Propene is 10 to the 6 times faster than ethene, and 2-methylpropene, which creates a tertiary alcohol, is 10 to the 11 times quicker than ethene. The mechanism for this one is almost identical to the hydrohalogenation mechanism. A proton transfer first. Hydrogen goes to the less substituted. A carbocation forms. Water is going to act as the nucleophile. A carbocation is the electrophile. And there's a nucleophilic hug. And everything with the water comes along, including both hydrogens. And that oxygen is now positively charged. This is an oxonium ion. An oxonium ion forms anytime oxygen has 3 bonds to it. There's still excess water floating around, which can do a proton transfer. To get the alcohol. If you have dilute H2SO4, which means that there's more water, if there's water in solution, you will get a hydration product. If you remove water, so there's less water available, you will do the elimination. So this is based on Le Chatelier's principle. If there's a lot of water, so a dilute amount of H2SO4, much water around, it will hydrate. If there's not a lot of water, the H2SO4 can protonate this alcohol, make it a good leaving group, and perform an elimination. So concentration matters with the hydration reactions. There's a couple of practice problems here. We have acid plus water. We're going to add water across the double bond. A tertiary carbocation will form here. In this reaction, we're actually going to form a new chiral center because this is flat and the nucleophile can come in from either side. And there was a hydrogen added here. You don't need to add the hydrogen if you don't want to. I've drawn it in here so that you can keep track of where things are going. We'll also get the enantiomer. So this is a 50% mixture. It can attack from both sides. If there is another group on there, this may help in controlling stereoselectivity. This is the carbocation that forms. We have this isopropyl group that is pointing on the wedge side, which kind of creates some steric bulk on the wedged side. So the water is less likely to approach from the front side where this isopropyl group is. So the water is going to attack and add from the back side, and it pushes the methyl group here forward. This would be the major product because that isopropyl group is helping to control the stereochemistry. There are two practice problems here. Here we're adding water across the double bond. There should also be acid here. A chiral center is not created here. This is symmetric. In both cases, the hydrogen went to the least substituted carbon and the halogen or alcohol went to the more substituted carbon.